Hello and welcome to the 19th lecture on our course on photonic devices. On today's lecture, we're going to discuss a few different concepts associated with semiconductor lasers. So some of these concepts are the threshold current for laser oscillation, the differential responsiveness, and we're also going to take a look at additional cavities which are typically used in order to decrease the laser line width and also to obtain single frequency operation or single mode operation. So up until the 70s, it was not possible to use laser diodes with CW or continuous wave operation. So basically the lasers, or these types of laser at least, had to operate in pulse mode, right? So you have the emission of optical pulses by controlling the injection current, the forward bias current, so that it was a pulsed current, right? And this is basically because the current levels that were needed in order to overcome the threshold current, which is a concept that we'll see on this lecture, these currents were too high, and with such high currents, the device would heat and you have problems of this order, right? So only pulsed operation was possible. And around the 70s, with the invention of the double heterostructure, it was possible to decrease the width of the active region of the active layer significantly, because instead of using regular p-n junction, right, or p-n junction, homo junction, which has a depletion layer of the orders with a width of the order of a few microns, it was now possible to use a heterostructure in which the middle layer, the active layer, has a width of around a few hundred nanometers, so around 0.1, 0.2 micrometers, right? So one order of magnitude smaller, at least. Plus, using lateral guiding with the advances of the fabrication technology and so on. Also the other dimension associated with the active region, right? The lateral dimension, which is associated with the lateral confinement of light, can be of the order of 10 micrometers, which is pretty small. So by using, all of these improvements, the transparency current was reduced by around 2 orders of magnitude. So typical values that we have nowadays are around tenths or hundreds of milliamps instead of fewer tenths of amps. And again, right, this was basically because with the invention of the double heterostructure, the device went from being something like this, right, a regular homo junction in which the depletion layer is, this dimension right here is of the order of, say, 2 microns or a few micrometers. And with the use of the double heterostructure, because the middle layer here is deposited or grown, you can control its width much more precisely. And also, due to the fact that you have these potential barriers that we've discussed previously, you have carrier confinement inside the active region, reducing even more the transparency and threshold current, because it is now possible to have carrier concentrations for electrons and holes in the active region which are much higher. The main advantages of the double heterostructure lasers, which allowed for these advances to be possible, are listed here. The first one is the optical confinement, because typically what happens is that, as a general rule, the refractive index of a material rises inversely with its band gap. So the smaller the band gap, the larger the refractive index. So in a structure like this, which would be a typical double heterostructure, right, in which the center semiconductor here, the active layer, is made in such a way that it has a smaller band gap, and the reason that this is done in such a way is in order to have carrier confinement, because of the potential barriers and so on. But This also comes with the advantage that this middle layer here, because it has a smaller band gap, it will also automatically have a larger refractive index, and therefore you can make a waveguide out of this, because you have, just like in an optical fiber or in other types of waveguide based in total internal reflection, you have a high refractive index material sandwiched between two lower refractive index materials. So light is more tightly confined in this middle layer here than, say, in this type of structure, right, where the difference in refractive index is much smaller. So this is one effect, right? You have much tighter light confinement in the active region, which is the region that has gain. So this is one benefit of the DHS. Carrier confinement, the electrons in the holes are trapped in the active region. So if, as illustrated here, you forward bias this, the electrons in the n-type material will tend to move towards the center material, the active layer, but they will have a hard time overcoming this barrier right here. Therefore, most of the electrons will be confined here. And the same thing will happen to holes, right? Due to the electric field from left to right, the holes will move in this direction, but they will find this barrier right here, which is hard for holes to overcome. Therefore, we'll have, in a small region of space with a width of hundreds of nanometers, a very large carrier concentration for both electrons and holes, much larger than you would have in a homojunction. So that's another factor that contributes to the decrease in the transparency and threshold currents. And finally, you have a device that absorbs less of the emitted photons, right? Since the gap of both P and N, heavily doped P and N regions, is larger than that of the active layer, the former do not absorb light. The former meaning the outside layers here. So basically we're saying that the emission will happen because an electron in the active region will recombine with a hole in the same region, right? And the energy of the emitted photon, as we've mentioned, is going to be equal to the delta E, which is close to, some value close to the gap in this middle layer right here, the active layer. But this other semiconductor here has a gap, which we'll call EG dash, which is greater than EG. And this is done on purpose, as we've said. But this also has another benefit, which is the fact that this photon with this energy here, right, which is emitted here, cannot be absorbed here, because in order for it to be absorbed here, it would have to be absorbed by an electron that is sitting down in the valence band, but since there is no energy level right here corresponding to the delta E, which is the energy of the photon itself. So because there is no level right here, it would fall within the forbidden band gap. Therefore, this layer cannot absorb the photon generated here, and this layer cannot absorb the photon generated here. So absorption will only occur in here, which is not true also for a homojunction, right? The photon could be absorbed anywhere within the device, so the absorption of the emitted photon would happen with a much larger frequency. So all of these advantages are critical in making double heterostructure the standard, which allowed for miniaturized semiconductor laser diodes to be used in optical communications, consumer electronics, and in all of the devices that we see them used today. Now let's talk a little bit about the lateral confinement, right? Because when we're talking about, sometimes we call this the width of the depletion region, but as we said before, right, typically these layers will be deposited on top of a chip, at least in some of the devices, and therefore you could think of this dimension as a height also, although it's common to call this the width when you're talking about, you know, the diode. But in terms of the way that it's constructed, you could think of this as the height, but you have another dimension where light is confined. And with respect to this other dimension, you know, the lateral dimension, the laser can be gain guided or index guided. Okay, and these are illustrated here, right? So one type of gain guided laser diode and index guided laser diode are illustrated on the left and on the right here. So what you have here, you know, this is a metallic contact, and you have the substrate right here, and the heterostructure is composed of these three semiconductors. So a p-type indium phosphide and an n-type indium phosphide layer on either side of the active region, and the active region, which is a smaller band gap alloy, which is indium gallium arsenide phosphide in this case, right? This has a smaller band gap, typical double heterostructure, and so the diode is formed in this region. This oxide layer, silicon oxide layers here are just dielectric, so you have no current flowing through these lateral dimensions here. The current would flow through the device here, and as the current flows here, because of the increasing carrier concentration, you have automatically an increase in the refractive index, which is another effect that also happens and contributes to light confinement, right? So basically light will stay within this region here and not, you know, leak towards the lateral dimension right here, because once the current is flowing in this direction, if you forward bias the device, right, current would flow in this direction, the excess carrier concentration due to the current density J will make it so that this region, which has a larger carrier concentration, has a slightly larger refractive index than these lateral regions of the active layer on either side. And therefore, this is why this device is called gain guided, right? Because basically the gain, which is due to the excess carrier, is responsible for raising the refractive index. So the free carriers make it so that the refractive index is slightly larger, and therefore light is confined in this way, right? So the cavity would be towards, in this depiction we're seeing the cross section of the device, and you know the surface of the chip is this dimension right here, is this plane, the horizontal plane, and the optical cavity is towards the screen, right? So you could have a mirror on either side in this dimension, you know, perpendicular to the screen. So light would propagate in this direction, and it would be guided both in the vertical and in the lateral directions because of gain guiding, and you know, in the vertical direction because of the double heterostructure itself, as we've discussed. So the advantage of this type of guiding is the fact that it's a simpler structure to fabricate. If we compare this to the index guided device, we see that this device has many more layers, right? So all of these layers have to be selectively deposited by different deposition techniques and using photolithography and etching and so on. So it takes a much larger fabrication effort in order to fabricate this device, because the active layer is only here, and you have additional, you know, p-type semiconductors and n-type semiconductors deposited on the sides here, and here, right? And this, you have an n-type here, an n-type semiconductor here, right? So this would also be a p-type indium phosphide, and this would be an n-type indium phosphide as well. And this is placed here so that you'd have a reversely biased junction here and here, and this prevents current from flowing here. So current would flow through here, right? But in terms of the optical confinement in the lateral dimension, this is achieved by index guiding here, because again, the active layer, the alloy indium gallium arsenide phosphide, which has a smaller band gap and therefore a larger refractive index, is only in this region, right? All of the surrounding media are composed of indium phosphide, doped indium phosphide, which has a smaller refractive index, and the difference in refractive index here, because it's different materials, you know, the increasing refractive index is not due to free carriers, it's due to the fact that it's a different material, a much smaller band gap, so the refractive index is larger, and this is the reason why this confines the mode much more effectively. So, but again, right, at the expense of a device which has a fabrication effort which is much larger, clearly. So this is index guided and this is a gain guided device, right? Another advantage of the index guided structure is that the field distribution does not depend on the intensity of the injection current, right? So basically the difference in refractive index between this region, so let's call this the refractive index of the active region, and the refractive index of the surrounding medium, which will basically be the refractive index of indium phosphide, is much greater than the difference in refractive index between this region and the lateral region right here. As you vary the direct bias current or current density J, the variation in the refractive index here would be insignificant when compared to the difference in refractive index between the active layer and the surrounding medium. Whereas here this is not the case, right? All of the refractive index between this center region right here and the lateral regions of the active layer is basically due to the excess carrier concentration. And as you increase the current, as J increases, this refractive index difference will change, will be more pronounced. So as you change the bias current, the guiding conditions will change dynamically, and the extent or the size of the mode in the lateral dimension will change as the current changes, which will not happen with this type of device, right? Again, right, this comes at the expense of additional fabrication steps, right? Now let's talk a little bit about the threshold current, IT, or I lowercase t, of a laser diode. So this is the current in which the laser effectively starts to oscillate. So there are two important currents here. The first one is the transparency current, which we've discussed at the end of our last lecture, right? And the transparency current is basically the current for which the excess carrier concentration inside the active region makes that region transparent, right? So it neither has gain nor it absorbs. It is basically transparent. So if you increase the current to a given level, you can think about in terms of the rate of emission and rate of absorption. So basically the rates of emission and absorption will be equivalent, and it is as if the medium was transparent. A beam of light that was passing through it would pass through without being absorbed at all, because the quantity of emitted photons per unit time would be the same quantity, average quantity of absorbed photons per unit time, and therefore the power at the output would be the same as the power at the input. And this happens because you raise the rate of emission by raising the the excess carrier concentration, which is proportional to the current, up to a certain level in which the emission rate is equal to the absorption rate. So that is the transparency current. But the threshold current, on the other hand, as we've said, is the current for which oscillation starts to occur. And for this to start to occur, the peak gain has to be at least equal to the cavity losses. So this is not, the peak gain does not have to overcome the absorption losses. Now the peak gain has to overcome the cavity losses. So all of the scattering losses due to Rayleigh scattering, scattering in the sidewalls of the optical waveguide, which is formed in the active region by the means that we discussed, previously. And the losses at the reflectors of the laser itself, right? So if it's a Fabry-Perot laser, it will have cleaved facets on the chip, of which the beam of light will bounce off. But some of this beam will inevitably escape the laser, right? And I say inevitably because you usually build a laser in order to take advantage of the light that you extract from it. So at least one of the facets, or at least one of the reflectors of the cavity will not have 100% reflectivity, perfect reflectivity, because you need to take advantage of the light coming out, right? So all of these losses are taken into account inside the cavity losses. And the threshold will occur when the peak gain is actually larger than these losses, or more precisely, the peak gain coefficient is larger than the attenuation constant of the cavity itself, right? So, and typically the threshold current will happen for current values that are 10% on average, or 10% above the transparency current. Therefore, we can write that approximately the threshold current, so I lowercase t, is 1.1, around 1.1 times I capital T, right? This is the transparency current, and this is the threshold current. Okay, so this is typically what happens. And above this threshold current, the relationship between the power that's emitted and the injection current is pretty much linear, right? So what we have is something like this, right? We'll take a look at actual measured curves on our next slides, but you have a first quasi-linear region right here, in which basically spontaneous emission is dominating. So basically the device is behaving like a light emitting diode, right, in this region, and it's not emitting much light. But as you increase the current, the emitted light increases linearly, as we've seen in light emitting diodes. But once the current reaches the threshold current, which is of the order of tenths of milliamps, and this depends on the temperature and on the device, of course. But once it reaches this point, the number of excess carriers in the active region is enough that stimulated emission overcomes the cavity losses and all of the losses we've mentioned, and the laser actually starts to oscillate. So from this point on, we have another linear region, but in this region you have effective lasing, so emission of coherent light or oscillation by the laser itself. And an important concept here, so this only occurs above the threshold current. And an important current concept that we'll see next is the differential responsivity, right, which is basically the slope of this part of the curve in which this linear region, which corresponds to the laser oscillation. So this is the differential responsiveness, also called the slope efficiency, and it's basically the slope of the power versus injection current curve above the threshold, right? It's basically the derivative of the emitted optical power with respect to the forward bias current of the laser diode. And it's therefore, since this is a straight line, it will also be delta P over delta I for a given pair of points that you pick along this line. But by definition, it's the slope of this line, or in other words, the derivative of P with respect to I on this graph, right? So that's the differential responsiveness. Okay, it's an important concept in it, relating to the efficiency of a laser, right? The increasing power with the increasing current that you have once the laser is actually oscillating. But the threshold current has a very strong dependence on the temperature, and we can grasp this by taking a look at the equation for the threshold current that we've just seen, right? So IT is equal to 1.1 times I capital T, the transparency current, and we can write the transparency current as a product of the transparency current density, right? Density per square centimeter multiplied by the cross-sectional area, right? So this is just another way to write the current IT. It's equal to the current density times the cross-sectional area, with respect to the area of the cross-section that's perpendicular to the current flow, right, in the PN junction. And we've seen an expression that relates the current density, transparency current density JT, to the transparency excess carrier concentration delta NT at the end of our previous lecture, right? So if we isolate JT here, we'll have what? JT is equal to delta NT times, the charge of the electron, times V, the height of the active layer, divided by tau, right? And if we plug this in here, in place of this JT here, this is what we get. So IT is equal to 1.1 times delta NT times E times the height of the cavity times the cross-section divided by the recombination lifetime. So basically what we take from this equation is that the threshold current grows in inverse proportion to the recombination lifetime. And let's recall that 1 over tau is equal to 1 over tau r plus 1 over tau nr. So this is the radiative recombination lifetime, this is the non-radiative recombination lifetime. And what happens as you raise the temperature, right? If the temperature increases, the non-radiative recombination lifetime will decrease because the rate of non-radiative recombinations will increase. So basically, as you increase the temperature, the atomic vibration inside the solid will increase. So the atoms will move around at a faster pace, with a wider movement along as time goes by. So the atoms will move around more as you increase the temperature, and this will increase the probability that non-radiative recombinations can occur, because again, right, usually when you have non-radiative recombinations, the electron which is up in the conduction band recombines with a hole without emitting a photon, and the energy is given off as a phonon, or some sort of mechanical form of energy, right? And as you increase the atom vibration or the temperature of the solid, this makes it more likely that these non-radiative recombinations can occur, because the atoms are vibrating with a higher energy, and therefore, the non-radiative recombination lifetime will decrease because the non-radiative recombination rate will actually increase and the fact that this will decrease will make it so that this will decrease as well, right? So if the recombination lifetime decreases, the threshold increases as you increase the temperature. So that's the way to think about why this happens. But the fact is that as you raise the temperature, the threshold current will increase, with temperature, and it will have a very strong dependence on temperature. So we can see this by looking at a few curves for the measured light emitted at the facet of a Fabry-Perot laser in milliwatts as a function of the current in milliamps, right? And we see here for different temperatures, so 10 degrees Celsius, 20 degrees Celsius, and so on, up until 130 degrees, that the threshold current, which for 10 degrees Celsius would be around this point, for say 70 degrees would be around this point right here, and for 130 would be this point. The threshold current changes drastically as you change the temperature, right? So let's say that you have a laser, you have your heterostructure, your PN, with the active layer, which could be a P-type material. You have your laser diode here, and you forward bias it, apply a direct current, and let's say that you polarize it at a current equal to, say, 45 milliamps, right? So on this point here, this would mean that if we were at room temperature, we'd be sitting on this curve right here, which corresponds to around 30 degrees C, or the one above it, in either case. So we'd be in this curve right here, right? So right at this point, and the power that's emitted by the laser would be around, say, 3 milliwatts, right? So if the temperature changes, let's say to 40 degrees C, right, or to 20 degrees C, you see that you would actually be moving along this vertical line right here, and the emitted power could go from, let's say, that the temperature went down to 20 degrees C, that the emitted power could go up to 3.3 milliamps instead of 3. So you see that it's very dependent on the temperature, right? And depending on the polarization point, the current, as you change the temperature, you could even go below threshold, and the laser would stop emitting light altogether, right? Or would only emit light like an LED. In other words, would emit non-coherent light with a power that's much smaller. So a laser emitting light at a given power could even be brought to a point below threshold with rise in temperature, just emphasizing that the temperature dependence of these curves is very large, and therefore for this reason, especially for optical communication applications, laser diodes are always fabricated together with Peltier type temperature controllers. So on the same chip you have some control mechanism for cooling the device and keeping the temperature steady, because otherwise this is what happens, right? You would be moving along a given vertical line here, and the power at the output would vary dramatically with temperature, and that's the reason why temperature control is important. This would not be as important, let's say, in lasers used for other commercial applications such as laser pointers and other things like that, but for sources used for optical communications, this is a very important aspect of the design of the device.